Okay, hi, this is Michael Ellis, and I'm really super excited because I get to show you something amazing. So, this is my last video. I showed you this, I went through this 555 pulsar circuit that I have running about 343, between 340 and 390 hertz, or 360, 390 hertz in there, because it's like the tolerance is not perfect. I actually got my probes, my new probes, because my old ones were kind of crap, so just from use and stuff, so I can actually measure it now and show you the actual waveform that's coming out of it. But anyway, so like here's my pulsar running. Obviously I'm like, that's an old battery. So I got my 9-volt battery running it. You can see the little LED output there. But now I'm going to show you the waveform that comes out of it and how it works. So we've got the thing pulsing. It's got a square wave coming out of it, and this is the output right here. This is the this yellow thing right here is the signal ground, which is just the ground of the battery, and this one right here is the I think, if I've got that right, yeah, this with this diode here. I'm using a diode, so just that shouldn't be down there, so it doesn't short out. Okay, this is the signal plus. So this is coming out of whatchamacallit, pin number 3 of the 555. So that's the output square wave. So I'm using a diode just to cut it off so it doesn't go back, so the current doesn't go back in and destroy the IC. Because we're pulsing it into a, and if you see here, red and black, they go into the to this like a audio transformer Torus Torus transformer thing. And if you look at the pins here, it's so it's just a square wave with a positive offset, and the if I can see, get that focus. It's kind of, the light's kind of hard to see that. Black and red are 0 to 12 volt, which is, we're doing 9 volt ish, and then the orange and yellow are the 2 low voltage inputs, and then the blue and gray, which I'm going to be using, is the high voltage outputs. So to give you like a little picture of what actually is going on, I'm going to attach the ground pin of my probe to the ground pin output of the coil, or not the output of the coil, but the input of the coil, just so we can see what's going on there. And my probe is on 1x, so it's a real voltage. I'm going to attach it to the positive side of the transformer there. And I have this at 5 volts per square, so you can see the yellow. The yellow is the battery here. So we got the negative and the positive of the battery. Don't pay attention to that or that. These are just holding clips for the output, as you saw the Fred zapper that I showed you in the last video. So this is actually the square wave going in and bouncing back out of the coil. So that's creating a nice little DC impulse there, bouncing positive and negative as the square wave goes in, and builds up the wave, and the wave collapses, and that's happening at approximately the frequency of, if I can zoom it in a bit, and if it focuses, we'll be in money, we'll be in business. Focus. Okay, 345 hertz is approximately the frequency we're getting back out of that. So the square wave, as we know, is like full of like tons of harmonics, so it like auto resonates anything. And so 345 is there, and we're getting approximately 5 volts on the little spikes. So that's what's happening, and the center is the center line there. So it's not quite reaching the voltage of our battery, and it's going negative, so it's not going to obviously charge our battery or do anything to our battery, as I've tried hopelessly many times in many different forms to actually charge a battery with that. But we are using AC, so we can use the transformer to try and charge our battery, because we're smart like that. We're electrical engineers, and we know transformers are what you use to... No, I'm just joking. Actually, we don't know that, but transformers we use to create higher voltages. And I have an inkling that higher voltages might just charge our batteries. Maybe. So let's see if we can do that. So okay, so here's our high voltage outputs. They're AC, obviously. So and they're high voltage based on the DC input. We're throwing in our whatchamacallit, throwing in our Torus, or alternating current thing. So you look at that, and suddenly we're in business. Look at those high voltage. They go off the screen even. Those are like beyond 10. So as you can see here, the battery is at 8.6 volts. The big lead acid 20 amp hour 12 volt battery is at 8.6 volts. So it obviously is in need of a charge. And look at those. Oops, we lost it. Where did our signal go? Is it even working? Are we getting a signal? Okay, there we go. So look at that signal. That's insane. That's some insane stuff. So it's obviously got a good on the DC side. It's got a good 7 volts maybe, like AC wise, and then it's got the spikes on it too. So so that's just insane. So being a good practicing electrical engineering student, we will use our DC charging circuit to charge our batteries. So we're going to convert AC into DC as much as we can using a bridge rectifier made out of LEDs, because that's all I had at the moment, and a smoothing capacitor, also known as a electrolytic capacitor, just in between the positive and negative poles of our AC to DC converter to smooth out the waveforms and stuff. So I'll just disconnect that. We're going to take our signal and we're going to put it through the AC part. And this is really hard to see because it obviously doesn't have the positive or negative markings on it. But here, maybe I can draw you a picture of this. Let's see. Let's draw a picture. So basically what we're doing is we're taking the AC and we're putting it out in DC. So we're turning AC into DC, the positive and negative, the AC. So we're going like this. So we're taking 2 diodes out. That one's really bad, sorry. Diodes, AC are pointing that way, and AC and DC negative is pointing that way. So as it oscillates back and forth, it creates a nice little DC impulse. And then we're going to put that on top of our capacitor. So our capacitor is going to go to the positive plate and sorry, I'm trying to do this on the negative plate. So it's going to charge our capacitor like that. And it has some resistors in the middle, but that doesn't matter. Oh, where's my cap? Where's my cap? Put the cap on this. Jeez, I'm a mess. Okay. So we got our insane signal. We're going to put it through the... So you can't actually tell, but I can't actually tell either. But I got this hooked up, so I guess the little this is the cup and spoon. I think that's what they call it. I don't know which one is which. My electronics professor called it the cup and spoon, but I don't know which one is which. Anyways, so the small one is the positive, apparently, because I have it hooked up to the positive side of our capacitor, and the black is negative. As you can see, we have it hooked up to the negative side of our capacitor and resistor, so we don't burn out our LEDs, and the cup side. Oh, the big one's the cup, and the little one's the spoon. So the cup is hooked up to the negative, and the spoon is up to the positive, as you can see there. So the spoons are positive, the cups are negative. And because you use the spoon to stir, so that's your positive. And the cup is the receiving, because that's the negative. That makes sense. That's how he remembers it. Okay, so that makes sense. Okay, so you have the cups on the negative side, DC side. Both cups are going towards the negative, and both spoons going towards the positive on the oh wait, did I get that wrong? Oh yeah, that's the positive. Okay, so both the spoons going to the positive on that one, and positive to negative on the AC side, and positive to negative on the other AC side. Okay, so we're gonna take that, and we have resistors, so we don't burn out our LEDs or destroy our batteries or any of that loveliness. So we have the output of our transformer, and we're going to hook that up to our... Wait, where did my... Oh, I was going to use my... Okay. So we're going to take that with our electrodes. Green means... well, actually, I'm going to have to use green for positive in this case. So I'll hook that up to that. Actually, I should hook that. So green we'll have to use in positive, though I know all I have is green and black with me today, so green we'll have to use in positive, even though it's normally the ground color. So green is our positive, and it will go on our positive side. Well, actually they're both AC, so I guess it doesn't matter. So actually it's not positive, it's AC. What am I saying? Okay, I'm not even thinking. They're both AC, so they're both AC. So we're using our AC, and oh, look at that, it comes to life. Oh, sorry, you didn't see that. Okay, I was naming it with the camera. Sorry. So it comes to life. So that's the nice thing about using LEDs as in a... Oops, got disconnected. Let's see, get that reconnected. This is a bad clip. Okay, there we go. So it comes to life. So let's measure it with our probe and see what's going on. So we have our negative down on the bottom. Our collection, and there we even add more life to it. I think those are cups. And then the spoons. Well, anyways, the positive of our... and then we have the positive coming off of our Wait, that's negative. Is that negative? Oh, shoot. I got those backwards. Didn't I? Oh, yeah, this is our positive. Sorry. I got that backwards. Okay, so we got the negative. There's our negative. Okay. Okay, if I actually pay attention to the markings here. Okay, so we've got our negative of the capacitor, then the positive, I'm sorry, you can't see, positive coming off our capacitor into a resistor, and we'll hook that up. And what happened? Oh, look at that. Our capacitor is negatively charged. What's up with that? Why is our capacitor charged negatively? Looks like we're dealing with negative energy. And that's all I'm going to share with you today. Because we've got it hooked up right. This is on the negative side. And this is on the positive side. And it's charged up. But it's negative energy. It's charging the capacitor backwards. It's charging our probe backwards. What? Da-da-da. Let's solve the mystery later.